Let's take a couple minutes here to talk about work in physics. And this is specifically going to matter because it's going to tell us how energy changes or how we create energy changes in a system. So work. Um, Work occurs when a force is applied over a distance. This is the definition of work in physics. So it's different, like a lot of the words we use, it's different from how it's colloquially used in English, but work is always when a force is applied over a distance. And specifically, we would say that work is equal to the force that's parallel to the displacement times some displacement delta x. So note, we need to use the parallel component of force. So the one that's parallel to the direction that we are traveling. So if I have something like I'm pulling with a force like this, and so the horizontal component here is F cosine theta, and if the object actually moves horizontally, it would just be F cosine theta times delta x. And typically, because of the way the angles are measured, it's often going to be F cosine theta times delta x, but not always. If you want to know kind of more clearly what's going on here, or more precisely mathematically, it's actually F times the dot product of our displacement, if you remember dot products. You don't need to know this for the AP Physics test. They don't ask about it, but if you're wondering kind of why it's ambiguous maybe or unclear, it's because it's the dot product. Okay, so let's talk about some of the properties of work. So work is a scalar quantity, and that's because it is the result of a dot product. Its variable is, as you saw before, the capital W. And the units for work are Newton meters. And that's written as a big N times a little m. We will see that this is equivalent to another set of units later, but for now we're just going to think about work as Newton meters, because fully properly it is, that's what work is in Newton meters, but we'll see later how we can use other units as well. So let's look at an example here. Consider a 3-kilogram briefcase. A person lifts this briefcase 0.75 meters vertically from the ground. They then carry it for 10 meters horizontally. Finally, they walk up a 30-degree ramp that's 2 meters in length. For each segment of the journey, how much work does the person do on the briefcase? Assume in each segment that the briefcase is moving at a constant velocity. So in the first part, while the person's lifting the briefcase, we know that they have to be counteracting the gravitational force. So the force of the person is equal to the force of gravity because it's moving at a constant velocity as it's being lifted. So the force person is equal to force gravity is equal to the mass of the briefcase times g. And if they're lifting it 0.75 meters vertically, their force vertically is the same direction as the change in position, as the change in position. So the work is going to equal the force of the person times delta x. They are parallel, so that will mean that it's equal to mg delta x, which is going to equal 3, let me write this out more properly, 3 kilograms times 9.8 meters per second squared times 0.75. And so that will be about 30, 3/4 of 30. So that's an 8, 7 something 21-ish Newton meters. And remember, kilograms meters per second squared is a Newton, so that gives us nice for about 21 Newton meters. For the second part of their journey, the person is still pulling upwards and gravity is still pulling downwards. And if they're moving at a constant speed, there's no horizontal forces at play here. It did take some horizontal force to get the briefcase moving horizontally, but now it's inertia carries it horizontally. So how much work is done here? If our delta x is equal to 10 meters, well, now if we look, how much of this vertical force is in the same direction as the horizontal force? Work equals force person parallel times delta x. Well, the work is equal to 0 times 10. 0 newtons times 10, because the person is not exerting any force horizontally here. They're just exerting the vertical force to hold the briefcase up. So in other words, in this second section, 0 Newton meters of work is done by the person carrying the briefcase. And again, that's because the person is not exerting any force horizontally. Okay, lastly, if we have the person exerting a force upwards, again, because the briefcase is moving at a constant speed, but this time our delta x is at an angle. So how much of this person's force is up the ramp? Well, let's figure that out. So we have the vertical of their pull, and then we have some component up the ramp like this, some component out of the ramp like this. And looking at that, that'll be 90 minus theta, that makes this theta. So it will be FP sine theta in this example. And again, that's just from reasoning out what theta angle is, which I figured out by drawing my triangle like this and knowing that therefore this bit right here is 90 minus theta, which means that top angle becomes theta. So in this case, we have work equals force person parallel times delta x. Work is equal to FP sine theta times 2 meters. And I'll leave that to you to finish solving it. It's just sine of 30 times mg, the same as before. So this is FG. But what you can see here is in all three cases, a different amount of work is done. The most work was done kind of proportionally when you were pulling in the same direction that you were traveling. No work is done if your pull is perpendicular to the direction that the object is moving, and some medium amount of work if it's at an angle to the direction that it's moving. Obviously, the closer it gets to the same angle, the more work gets done. So that's an introduction to work.